Hi, I'm Srini, and I'll be talking about probabilistic data structures and how we can use it to do real-time log analysis. So this is more like tutorial slash patterns that you can use to analyze logs, right? So that's what this talk is about. So about myself, I work with multiple startups, helping them build products from scratch to launch and then scale more. So, these are all the tools that I use and love building such stuff. So basically about the problem, right? The previous company that I worked for was into the retail domain and they were building products, specifically recommendation engines and different kinds of automation tools for the retail e-commerce companies. And they were having multiple microservices, and all these microservices were generating lots of different types of logs. And the usual way, this is a more simplified diagram of the usual way people analyze logs, right? So all the user events or any kind of data that is generated is all pushed to a Kinesis firehose, and then you try to ingest it all into an Elk stack, right? So Elk is Elastic Search, Logstash, and Kibana. So that is the usual way people do it, and that's what we also tried initially. And the problem was the team was spending few weeks to get it configured properly and everything done right. And the second problem was it was bloody expensive, because to run to do proper setup with multiple nodes, we were spending close to like slightly more than $5,000 per month. And I want to show a little bit of the kind of data that we were logging. So, for example, let's say this is the log that is generated when a user visits a particular product page. So there is an action, there is a user ID, there is a product ID, and of course there's IP address, lots of these things. And similarly, there are each layer in the entire system generates these kind of logs, and we were logging close to like 50 to 60 data points, and we wanted a way to derive some kind of insights out of this. So the problem was, when we tried first for a single customer, on day one they started generating like hundreds of millions of log events every day, and they were like pushing logs. We were like unable to do a real-time analysis on the fly, right? So that was when I said, okay, Redis is fast. Why don't I try using Redis to process some of the logs, right? So I told the team, you guys work on your Elk stack solution, and let me try doing something on Redis and see how it turns out. But the main thing we want to optimize is, of course, in this diagram, you are given the choice of using only two, right? So you want to make sure your costs are pretty low, and scale is something that you can't decrease your scale, because the logs are generating, and you can't ask the customers not to use or users not to visit the site, right? So the only other variable that we can play around with is accuracy. And the way you can, there are two types of accuracies that you can play around with, right? So one is on the temporal side, where you can say, I don't want real-time data. I can do it in a batch processing mode, or maybe I will catch up later, and so on. So that is one way, but we do want to have real-time information. And the other way you can play around with accuracy is the actual accuracy of the data, right? And probabilistic data structures are one of the amazing things that I found that are pretty neat, where you can get pretty fast data structures, but as long as you're okay with inaccurate data out of your data structure, I think you should be okay with probabilistic data structures, because probability by nature is not accurate, right? So when I said, okay, let's see if there are any probabilistic data structures that are there in Redis, of course I did find that with Redis 4.0, after the module system was all built, people started building a lot of such probabilistic data structures, right? So this is a quick introduction of how you can use modules, load modules, and so on. So basically, you go to the GitHub page of the module, you compile it, create a module.so file, and there are 3 ways where you can load it. So while you're starting your Redis server, you pass the load module option and pass the path name, or you use your load module directive in your redis.conf file, or the other way is dynamically load your module during runtime. So these are the 3 ways that you can load. So what modules does is it adds extra commands to your Redis server. So the usual commands that are available on Redis, they work fine. But when you have extra commands, the way you execute those commands slightly differ. So for all my examples, I will be using Python and the usual Redis package, the Redis Python package. So when you have modules that you want to, the custom commands that modules expose, this is the way you use. So you call the execute command method and you pass the module command and then the parameters that are needed for that. So this is the way you execute your custom commands, right? So enough about modules and everything. Let's dive into the data structures themselves. There are like 4 data structures that I was primarily using for building the log analysis dashboard visualization thing. So first is Hyperloglog. Hyperloglog is not a module. Like it was, I think, introduced in 2.8.9. I'm not sure, but Hyperloglog is a way to count the cardinality of your set. So let's say you have a set of, say, 1 million items. If you want to find out the count of elements, the distinct elements in your set, you can either store them in as a Redis set, but that's going to take huge memory. Whereas if you store it as a Hyperloglog, you can get the count of the number of elements in the set, but the storage requirement is just 12 KB. And that is like a huge order of magnitude difference between megabytes of your key taking up MBs versus 12 KB, right? So that's a pretty neat data structure that was built into Redis. And also, you can add as many items that you can possibly think of. The number of items that you can add to this Hyperloglog is 2 per 64, I think. So, and the other best part was it has a constant error ratio. So every probabilistic data structure has some sort of an error ratio built in, and Hyperloglog in Redis specifically has an error ratio of about 0.81%. So even if you put in 1 million elements, your error rate is going to be 0.81 of 1 million. So with let's just see some examples, right? So I used Hyperloglog to count the unique visitors every hour. So the way you use Hyperloglog is you use the pf add command, and the syntax is pretty simple. You always start with the key that you want to use as a Hyperloglog. In this case, it's user and datetime are string, and the parameters you pass in are the user IDs you want to track. So I'm just saying in the 20th hour, there are 3 users that were added. And if you want to get the count of the number of users, you just do a pf count of your key and you get back the result as 3. And if you try adding the same user again, you get back a 0 saying the user is already there, right? So this is a very easy way to add users to, or count number of users. And the second best part about the Hyperloglog in Redis is you can merge multiple keys into one Hyperloglog. So this is really helpful. So like if you take all the hourly keys for a particular day, you can merge them all together and you get a daily key. And even if you have like all the 24 into 12 KB, your destination key, that is the daily key, is still going to be 12 KB. And that's like pretty amazing. And that was, I started rolling up hourly into daily and daily into weekly and monthly and so on. So it gives you real power, right? So this is the way you can use the merging functionality. So you just say pf merge your destination key and the list of all source keys. So I just given a simple example of 2 source keys and 1 destination key, and you can merge days into hours and so on. So it can you can play around with this. So these are the links related to Hyperloglog. The slides will be shared, so I have a link that you can go to get the slides. So the next data structure is top K. So top K is basically, if you want to get the top K elements in a set, you can use a top K. The usual way you would try to do it is, if you didn't have the specific top K implementation, you would have a sorted set of all possible items, and you will get the 0 to kth element, and you will return that back, right? But to store all the elements in a sorted set, it's going to take a huge chunk of memory. And top K solves that problem by making sure it takes only k log n space instead of n items. So that's the space complexity of the top K data structure. So this is how you can use a top K data structure. So you say top K dot add and the key that you want to use. Then you have 3, that is the K, how many elements you want to track. The top 3 elements is what I'm going to track here. And then I have an IP address that I want to track. So I just want to find out what are all the top IP addresses that are hitting my API. And this, I keep adding all the IP addresses as I keep getting all the log messages, right? So once the 3 elements were added, when you try to add the 4th element, it returns back a -1 saying one of the IP address was evicted from the top K set. So the way it is implemented is quite interesting, and there is a GitHub. You can check the source code, and it will be really cool way to know how it works, right? So behind the scenes, it is actually implemented as a sorted set. So you can just use a Z range or a Z rev range if you want on the key and get back all the values. But the 0th value is some kind of a binary blob which has all the information about the probability and all those things that the data structure needs. And this is how you can use top K. You can track the top K IP addresses or top K products that are popular in a particular day, or users that you want to see who are all the more active users and so on. So these are all the different kinds of use cases, right? So this is also available in GitHub. And the third data structure I want to explain is count min sketch. Count min sketch is basically a way to count the frequency of different items. So if you didn't have a count min sketch data structure, you would probably implement it as a hash map. So you would have a key and a value would be the counter itself. So you would, if you were to use Redis hashes, then you would be storing all the information of the counts for all the different items, and you would end up storing everything, right? But count min sketch does a pretty cool way to do that. So basically what happens is, this is a very simplified explanation. So let's assume that there are 3 hash functions, h1, h2, h3, and there are 4 values. So it's x cross y matrix kind of thing. So with this kind of setup, let's see few examples what happens when we add a particular item, right? So I'm adding one item S1, and the hash function returns 1, 2, and 3 for h1, h2, h3 respectively, and I just mark all those values as 1. I increment it by 1, and let's take S2, the second value comes in, and I mark the 4th element as 1, 1, 1, because the hash returns 4 as the value, so I mark those elements as 1. So the third value, S3, returns 1, 1, 1 as the hash values. So you increment the h1 1 row, so it becomes 2, and 2 and 3 becomes 1 and 1. So after adding S1, S2, S3, these are the 3, this is your matrix, right? So with this, let's assume that you're going to check for the, what is the count for S1. So you get back S1, you pass it through the hash, all the 3 hash functions again, you will get 1, 2, and 3, and the values for 1, 2, and 3 is 2, 1, and 1, right? And of these 3 values, you have to take the minimum of the 3 values, and that is going to be your count. Similarly, if you take S3 as, S2 as your count, right, you will get back hash values as 4, 4, 4. So in this, the last column is all 1, 1, 1, and the minimum of all these 3 values is going to be 1. So that's going to be a count for item S3. So if I can explain it better in example, right? So this is how you use the count min sketch in Redis. So there is a command called cms.incrementBy, and there you mention the key name and the item comma count pairs. So in this specific case, I am trying to find out the number of page views each user did. So in this example, the cms.incrementBy is the command. Then there is a u:pv:: string as your key, and there is there are pairs of user and counts. So 123 user ID did a page view of 1, and 456 user ID did a page view of 3, and so on, right? So with this, the values are stored in the CMS data structure in this format, and once it's all done, you can now do a query on the CMS data structure with cms.query, and you pass in the key name where you want to do the query, and you then pass the list of users for whom you want to get the counts, and it returns back a list of counts. So the values are accurate in this case because the data set we have added is pretty small, right? But when you keep adding hundreds of thousands of users, then there is going to be a small inaccuracy in the data structure. So this is how we use count min sketch to count the number of page views per user and number of number of add to carts that happened and so on. So these are all different use cases that we used. The other best thing about CMS is you can merge multiple counters together, and you just specify the command cms.merge, then you say this is the destination key I want to merge to. In this case, it is the month datetime string, right? And Then I specify how many keys that I want to merge together, in this case 3, and I say 29, 30 and 31 are the different keys that I want to merge together, and it is all merged together into the destination key. And the same way you can do hourly to daily and daily to monthly and so on. So this is a pretty cool way to do this. So you can check these links, and the second link has much better description about how this algorithm actually works and how they've implemented it and so on. And the last data structure I want to talk about is Bloom filters. So I actually started with Bloom filters when I started knowing about probabilistic data structures, and I've like used it a long time back. But to explain it, Bloom filters are a way to test membership in your set. So it helps to say whether a particular item was already seen or not. That's what Bloom filters does. But it is a probabilistic data structure, so there is going to be some kind of error, because the Bloom filter can say that it has seen it, but it might have not seen it actually. So I can explain how it actually works, and then you will probably understand it better. So you have an empty bit array. In this case, I have 16 size bit array, but in practical purposes you would have a longer size. So you start with this empty bit array, and similar to count min sketch, here also you will use different hash functions, and in this case I am using 3 hash functions, h1, h2, h3, and I am adding item 1 to the Bloom filter, and the different values that the 3 hashes return are 2, 5 and 8. So I mark these the second, fifth and 8th positions in your bit array. I mark it as 1 instead of 0. So this is, you keep on doing this for every item that you want to add. So for item 2, I mark the other 7th, 8th and 10th bits, and I keep doing that for every item that I see, right? So if I want to check whether an item exists or not, I redo the same hash for the same item. I check the positions that those 3 hashes return. For in this case, I say item 3, the hash values returned are 2, 11 and 0. I check for those positions. It shows that 2 of those positions are 0. That means that we have never seen this item before, right? So this shows that this item has never been in our set. But as you keep filling more items in your Bloom filter, as you keep putting in a lot of items in your Bloom filter, right, you start to get false positives. So basically this is item 4, and let's assume that the hash values are 10, 8 and 7, and you can see that those values are marked as 1, but we have never actually seen item 4 before, because item 4 item 2 and item 1 were the only things that we have added, but item 4, because of the hash collision, it returned back 10, 8 and 7, and we find that all 3 are 1, and the Bloom filter will return back saying, yes, this item it's possible that we have seen this item. So in Bloom filters, there is a possibility of false positives. So you have to remember that whenever a Bloom filter says false for a membership test, it says it is definitely not in the set. But if it returns a true, then there is a small possibility that it could be in the set or it can't be in the set, right? So Bloom filters, usually they are used for crawlers. Basically, if you want to hit an API, or if you want to crawl multiple websites, you want to make sure you don't bombard your site, right? So you have a Bloom filter and you keep adding the URLs whether you have seen it or not, and based on that they either crawl or don't crawl, or hit the API or don't hit the API. But in our case, for log analysis, right, the main use case that we had was we wanted to track the journey of a user over the different pages that the user viewed. So let's say the user viewed page 1, 2, 3, 4, and so on, and the time difference between two actions determined whether the user was in a particular session or not. So there are a lot more heuristics, but I'm giving you a very simple example. So let's say the user viewed page 1, 2, 3, and the next page view that happened was after an hour or something. Then we, according to our heuristics, we say that the pages 1, 2, 3 belong to one session, and page 4 and whatever that happens next belongs to the next session, and so on. So, and since, like I said, there are a lot more other checks that we do, it has to go hit the database, and it has to do a few more calculations, and we wanted to make sure that it was very fast to do this check. And we used a Bloom filter in front of the actual database, and we checked the Bloom filter and found out whether the session was active or not. And if the session was active, we then made the actual check and confirmed that the session was really active, and so on. So this is how we used Bloom filters. And the commands are pretty simple. There is a bf.add command, but I have used a bf.madd. madd stands for multiple add. If you use bf.add, you keep adding one user at a time. But in this case, I'm adding, for this key, add 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 user IDs, I'm just adding them to these keys. And once it has been added, I just have to say bf.exists. You pass in the key and the user ID. It will return back true or false, depending on whether we have seen this Bloom filter or not before, seen this user ID in the Bloom filter or not, right? And like I said before, you have to remember that there is a possibility of a false positive, and you have to, if it returns a true, you have to then do a check against that. And one more thing that you can do is, let's say your Bloom filter has a lot more elements and it has filled up, right? So the chances of hash collision is much higher now. You can stack multiple Bloom filters on top of each other. So you would add, once your Bloom filter 1 is complete, you will create a new Bloom filter key, and you will keep adding the new elements in that. And you keep stacking that, and that is called as scalable Bloom filters. And that's a pretty neat idea that I saw in this Redis Labs blog. And there was another, recently I saw this the last link, right? Instead of a Bloom filter, you can even use a cuckoo filter. It is a different data structure, but it does something similar to Bloom filters, but it has 2 or 3 additional advantages. One, in a Bloom filter, you can only add items. You can't remove items, because you won't know whether the bit was set by exactly this item or not, right? So you can only keep adding items. But in a cuckoo filter, there is a way where you can even remove items. That is one. Second, in the RE Bloom module of Bloom filter, the different hashes and the number of hash functions are all fixed, and you can't change them. But in the other Redis cuckoo filter module, you can have your own hash functions. So you can add as many hash functions as you want, and you can play around with that to get the right fit, right? So, but I haven't exactly used cuckoo filter before, and I just noticed this few weeks back, and it seemed to be quite interesting, because you can remove elements from the Bloom filter, right? So this is another interesting project that you can check out. So with this 4 data structures, we eventually did a pretty decent visualization kind of tool, and I did in a day I could create a Python Flask application, and it exposed a few APIs and a few numbers, and it was able to roll up hourly to daily and monthly and so on. And while the other team were still struggling with their elk and everything, we were able to do this. And we were able to run this on a large M3 large instance. I think it has about 6 gigs of RAM. and that's a pretty decent price when you compare it to the thousands of dollars that you would spend on an ELK cluster, right? So that was the advantages that we found. And I wanted to leave at this stage, right? So an 80% solution that you can get to working today is much better than a 100% perfect solution that you might get working tomorrow or later, right? So that's all I have today. So the slides are available in this link, so you can go there and you can download the link, the slides. Thank you.
Questions?
Just continuing the use case, what do you use for analytics of the data? After you store all the data, you retrieve the data, what do you use, what kind of tools do you use for analytics basically?
Can you repeat that? Sorry.
So what are you using for analytics once you've actually collected the data?
When you use analytics?
Yeah, what are you using for the analytics?
Like I mentioned, we were doing ELK stack. So basically time series analysis, that was one. We also did try using InfluxDB and Grafana. That was another stack that we did try around. But ELK had much more capabilities, like you can just throw in JSON and you can filter and group by based on different fields that are available in JSON. So to do proper time series analysis and lot more features, ELK is definitely the way to go. But this is a much more simpler and easier way to get quicker insights and things that you can. There was sort of like I started it as a pet project for a day, and that's how it went. So that's.
I have a question about the Hyperloglog. So if I want to save the log data into some kind of database like Mongo and want to retrieve later, so how can you use the Hyperloglog in Redis and retrieve the data from Mongo and do the instant query?
So Hyperloglog specifically only returns back the cardinality of the set. So you won't get anything else. You won't know what elements are in the set or not. So you keep adding things to your Hyperloglog, you will be able to get back only one integer saying these many items might be in this set. That's what Hyperloglog does. But if you want to store your logs in Mongo, but you can store it in Mongo and you can retrieve it whenever you want. That is a way. But these two are not related. So.
So regarding the Bloom filter, you mentioned there is a stacked Bloom filter as soon as the size reaches a particular threshold.
Yeah.
So that's managed by Redis. But if
no, it is not managed by Redis, but I don't think it is managed by Redis. Mm-hmm. So it was, the blog mentioned that this is a way to get scalable Bloom filters. You can keep expanding the number of elements that you want to put into Bloom filter.
Right, but if I'm using a library that Google has an Bloom filter implementation, so how do you define or how do you come up with the size of what your Bloom filter should be?
There are a few calculators that you can find saying you want to store these many items and you want your error rate to be say 0.01% or something like that, and based on that it will give you saying this is going to be the size of the Bloom filter and it's going to take this much memory and so on. And I think RE Bloom also allows you to play around with these parameters. So they are all optional parameters, but the default settings mostly works. So
okay, thanks.
Thank you.
Can you add number of hash elements while using Bloom filter?
Number of?
Like you use 3 of them, right? Can you add more? Like I would like to add 5 or 6 to make it distinct.
Yeah, sure, yeah. So the way you can make sure that your Bloom filter doesn't get a lot of hash collisions is adding more bits or adding more hash functions. And you can play around with these different parameters and you can do that.
So are there any adverse effect of adding that? Like if I have 3 versus I have 4 or 5, like is it going to vary my error rate?
Yeah, your error rate I think will reduce, and also the time taken to hash everything. If you have like 100 hash functions, it's definitely going to be slower. That is one problem. So.
Any other questions? All right. Thank you very much.
Thank you.